Greetings and welcome back to section 4.6, basis and dimension. Now this is a big section, and so I'm going to split it up into a couple different videos. So we'll start with basis. Now, if I give you, last lecture we discovered that 1, 0, 0, 0, 1, 0, and 0, 0, 1 was a spanning set for R3, but so is 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1. Now, which would you report as the spanning set for R3 if you had to pick one of them? Well, the answer is the shorter one, right? Because it includes all the relevant vectors and none of the irrelevant vectors. That's the idea behind a basis. A basis for a subspace is a set of vectors that spans that subspace. Okay, that's the first requirement. You have to be a spanning set. Then you have to be a linearly independent set as well. So that means you can have no redundant vectors. You want the smallest spanning set that you can find. Now, to find a basis for the span of a set of vectors. So let's say I defined S to be our subset, where S was the span of vectors V1 through Vn. That is a subspace. We proved that in a previous lecture. To find a basis for it, what we're going to do is take the vectors v1 through vn and make them the columns of a matrix. At that point, we'll row reduce that matrix, okay, and delete any vector whose column is missing a pivot, okay? So anything that has a pivot remains. Every column that doesn't have a pivot gets thrown out. The set of vectors that are left over is a basis for that subspace. So let's look at S and define S to be the span of the vectors v1, v2, v3, v4, and v5. Now I have listed the vectors right here is what they are, but we can kind of think of them as just the generic v1 through v5 at this moment. Okay. Letter A, find a spanning set for S. So if S is defined to be the span of these vectors, and you want to find a spanning set, well, the set of vectors that span S are going to be a spanning set for the subset. Okay? It seems kind of circular reasoning, but it's not. If we're defining a subspace to be the span of the set of vectors, then those vectors span that subspace. So the answer to letter A is V1, V2, V3, V4, and V5. That is a spanning set for S. To find a basis for S, what we're going to do is we're going to take all these vectors and make them the columns of a matrix. Okay, and I've done that down here. Okay. What I've also done is I've also row reduced that matrix for you. Okay, so we took this matrix here that had the columns, the vectors as columns, and we row reduced it to this matrix here. I've underlined everywhere where there's a pivot and every column where there wasn't a pivot. Okay, now what you can see is columns 3 and columns 5 do not have pivots. Okay. Therefore, those vectors, vector 3 and vector 5, are some linear combination of the vectors 1, 2, and 4. So that means using 1, 2, and 4, I can find a linear combination that gives me vector 3 and vector 5. Okay, so this tells me, okay, this is not my answer to part B, but this is kind of my thought process going forward with this. The span of vectors 1, 2, and 4 is equal to the span of vectors 1, 2, 3, 4, and 5. Because 3 and 5 are the redundant vectors. And because these vectors span S, then this set of vectors also spans S. But because there's a pivot in every column that corresponds to 1, 2, and 4, then it is also a linearly independent set. Therefore, since V1, V2, and V4 span S, and are linearly independent, they form a basis for S. So that's part B. A basis for S are the vectors V1, V2, and V4. Letter C. Find a spanning set from the null space of A. What is the null space of A? Okay, well, to do that, we take our matrix and we row reduce. Okay, well, we've already done that. Okay. So we start in our row reduced echelon form 1, 0, 4, 0, negative 3, 0, 1, negative 3, 0, 5, 0, 0, 1, 0, 0, 0, 1, negative 4, and zeros all the way down. Remember, this corresponds to the equations x1 plus 0x2 plus 4x3 plus 0x4 minus 3x5 equals 0. Okay, just looking at the first row only. So I can conclude that x1 is equal to minus 4x3 plus 3x5. In a similar fashion, I can say that x2 is 3x3 minus 5x5. x3 is equal to itself. It always is. Okay, and x2 is equal to itself, but I can use the information that's given to me in column 2 to tell me what x2 is. x4 is equal to 4x5, and x5 is equal to itself. You see what I did was I took all the columns that did not have a pivot. Sorry, that one does, that one doesn't. Okay, and I let those values be equal to themselves, whereas everywhere that did have a column, I wrote it in terms of the free letters. Okay. Now, any vector that takes this shape, where its third component and its fifth component could be anything they please, but the first, second, and fourth components are given as prescribed, when multiplied by this matrix A, outputs 0. So let's take this result. And notice that they all have, or most of them, have x3s and x5s incorporated in them. So I could take x3, okay, and write this as negative 4. Make sure you guys can see in the screen. This is negative 4 times x3, 3 times x3, 1 times x3. There's no x3s here and no x3s here, plus x5. And that would be what? 3, negative 5, 0, 4, and 1. So the set of vectors in the null space of A look like this, which are scalar multiples of these two vectors. So, because they're scalar multiples, and this is a linear combination, the span of the vectors 4, negative 3, 1, 0, 0, and 3, negative 5, 0, 4, and 1 is equal to the null space of A. Or in other words, and I'll write it in a different way, the vectors 4, negative 3, 1, 0, 0, and 3, negative 5, 0, 4, 1 span null A. So both those are true statements, and they both mean the same exact thing, even though they're written differently. Okay. Let's see what else. Let's see what's else. Find a spanning set for the null space of A. We've done that. Find a basis for the null space of A. Now, if we're going to find a basis for null A, first we need a spanning set for null A. This is a spanning set for the null space of A. Okay. Now, since there are only two vectors in my spanning set, all I have to do is make sure neither vector is a scalar multiple of the other. And this is only true for sets with two vectors in it, because when we're checking linearly independence of two vectors, all you have to do is make sure one vector isn't a scalar multiple of the other. Okay, and that's easy to confirm in this case. For these to be scalar multiples, okay, I would have to be able to multiply something, 1 by something to get 0, and 4 by something to get 0, and 0 by something to get 1. But it's the same thing that I'd have to multiply all this by to get that vector, and obviously that's not possible. Okay, so not only does this set span the null space of A, it forms a basis. These vectors form a basis for null A. That's the answer to part D. All right. Let's take a look at the next page. Example A. Is the set of vectors 2, 4, negative 1, and 1, 2, negative 3 a basis for R3? Explain. Now, most of these next 5 problems are just going to be problems that you're going to think through. You don't have to do a ton of work. In fact, you're not going to do any work for a lot of this. Okay. What is necessary to form a basis for R3? Okay, well, you take these vectors and you make them the columns of a matrix, 1, 2, negative 3. Okay? To form a basis for R3, the vectors must, 1, span R3, and 2, must be linearly independent. Okay. Looking at these two vectors, or looking at this matrix right here, how many vectors are required to span R3? Well, you need to have a pivot in every row. Okay, so I can have a pivot here and I can have a pivot here. Not saying these are pivots, but I'm looking at the possibilities where can I have pivots. But I can't have a pivot in row 3. So the first step is already violated. The vectors must span R3. This can't span R3 because I don't have enough vectors to span R3 because I can't have a pivot in every row. So the answer to part A is no, it's not a basis for R3. Okay, part B. is this a basis for R3? Okay, and what I've done is I've taken the two vectors above and I added two more vectors, 1, 4, -1, 2, 3, and 4. Okay, well, let's take a look. We have 2, 4, -1, 1, 2, -3, 1, 4, -1, and 2, 3, 4. Okay, can I have a pivot in every row? Could be a pivot, there could be a pivot, there could be a pivot. Okay, I'm not saying those, if we row reduce, that's where they would actually be. I'm just saying that's where they could be. Okay, so yes, okay, they may be able, vectors must span R3. Vectors must span R3. Okay, and the answer to that is, well, maybe we would have to check that out. 2 is that the vectors must be linearly independent. So if you look at linear independence, you can see that there's one column that must not, at best, there's at least one column that won't have a pivot. Now, there could be more than one column, but there's going to be at least one column that won't have a pivot. And if it doesn't have a pivot, these vectors are going to be linearly dependent. So this list is too long. There's too many vectors in this list for this set of vectors to be linearly independent. So part A, there's not enough vectors. Part B, there's too many vectors. How about letter C? Okay, is that list of vectors a basis for R2? Okay. Go through the same line of thinking. 1, 2, 3, -1, 2, 5. Okay, where can your pivots be? Okay, it can be here and here. Okay, can you have a basis? And the answer is no, because at least you're going to have one vector be dependent on the others. Okay, you can have more, but at least one, so that's not a linearly independent list, and if it's not a linearly independent list, it cannot form a basis of anything. How about D? Is D a basis for R4? So you probably already are answering these before I go through the line of thinking. 1, -2, 1, 0, 0, 2, -8, 8, -4, 5, 9, and -9. Look where your pivots could potentially be. They could be here, here, and here. Okay. Well, that leaves a row without a pivot. And if there's a row without a pivot, then that list of vectors cannot span all of R4. Therefore, it can't form a basis for R4. So here's the magic question that you've probably already identified by now. How many vectors form a basis for R2? Answer, 2. How many vectors are needed to form a basis for R3? Answer, 3. R4, 4. You got it. So that's the relationship. When you're looking to form a basis for Rn, you're looking to find n linearly independent vectors that span Rn.